Dimensionality reduction is one of the more complicated topics we discuss all semester. Students often have difficulty conceptualizing what the procedure actually does to their data. Based on high school geometry, we're all familiar with the notion of dimensions when discussing 1, 2, and 3-dimensional objects. However, we often don't think about the variables in our data set as dimensions, even though that's exactly what they are. To illustrate, consider this coffee cup. This is clearly a 3-dimensional object. However, it's possible to represent this object in 2 dimensions. If I were to ask you to draw this coffee cup, you would likely produce something like the following. Let's think about what we've done here. We've represented a 3-dimensional object in 2-dimensional space. This picture is not exactly a coffee cup, but it's recognizable as representing a coffee cup. I've done this exercise dozens of times, and people always draw roughly the same picture. Why? I could have drawn the bottom of the coffee cup. Alternatively, I could have drawn the top of the coffee cup. Why did I draw it the way that I did? It turns out that there's an algorithm at work. It's encoded in our brains, and it's something that we do naturally. The algorithm works like this. First, we find the longest path through the object. In this case, the longest path is from the front edge of the cup to the back rim of the cup. Length here represents information, so the longest path is associated with the most information. Next, we rotate the object around that path until we find the next longest path through the object. The second longest path in this case passes through the handle. These are the 2 most important dimensions to represent if we want to preserve as much information about the original object as possible. Drawn any other way, this 2-dimensional representation would not preserve as much information as possible and would be less recognizable as a coffee cup. This is exactly what principal components analysis, PCA, does. The goal is to reduce the number of dimensions while retaining as much of the original information as possible. To do so, it finds the paths through the data, called eigenvectors, and their associated variation, called eigenvalues, which are analogous to the length in the previous example. From these, we discard those dimensions that provide very little information, i.e., those that have small eigenvalues. Consider the following example. Assume we have collected information on the height, weight, and age of a group of people. We could represent the data using a 3-dimensional scatter plot, with each dimension corresponding to a given variable. Among these variables, height and weight are likely to be strongly correlated. As people become taller, they're usually heavier. Age would correspond more loosely to weight and would be unrelated to height sometime after the age at which people stop growing. If you think about it, height and weight both tell you the same thing, the person's size. Dimensionality reduction approaches like PCA might reduce this data from 3 dimensions, height, weight, and age, to 2 dimensions, where height and weight are mathematically combined into something we could call size, and another dimension that was more representative of age. Size and age still capture the majority of information that was present in the original data set, thus achieving the goal of dimensionality reduction. I hope you found this discussion of dimensionality reduction helpful. This is a complicated topic, so if you don't get it, review the materials on the course website carefully and don't hesitate to contact me with your questions.